My name is Ryan. I'm one of the co-founders of Foam. And Foam is a protocol that's focused on building a consensus-driven map of the world, blockchain-based protocol. And the protocol itself is made up of a few different elements, and really with the idea of bringing geospatial aspects into blockchain development. So these elements are a geo-encoding scheme for smart contracts, a visualizer, an API tool that's kind of like a visual blockchain explorer for geospatial data that's map-based, and ultimately proof of location. So how can we actually verify this data in a trustless and permissionless way? And when it comes to proof of location, we have kind of two types. And so the first is what we call static proof of location. And this is on verifying geospatial data that doesn't move, namely points of interest data. So currently, today live, we have on the Ethereum mainnet our first application, which is the Foam map. Ben mentioned token curated registries. So this operates as one where you can curate geodata, challenge people, and vote. And we call this static proof of location because it's about things that don't move. But really where we're moving is towards what we call dynamic proof of location. How do we actually verify things that move around, like a person, a car, or a machine? And that's really where IoT comes into the Foam protocol and will be the focus of this talk, is dynamic proof of location. And in this system, we use low-power radio beacons and a time synchronization protocol to make a terrestrial GPS system. That's an alternative, and I'll get into why. So in dynamic proof of location, we're looking for a consensus on whether an event or agent has verifiably been at a certain time and space. And the fundamental tenet of the whole Foam proof of location system is time synchronization. So we have these fixed radio beacons. In our system, we call them zone anchors. And they establish a zone of coverage, kind of like a time zone that we have today. And they maintain a quorum on time and space in that area. But before kind of like diving into how proof of location works, it's important to take a step back and think about how location works today. Because most people think of it as a solved problem and don't really spend too much more time on it. So how we actually find location today is through the GPS system, Global Positioning System. And the way it works is there's 30-something satellites out in space orbiting. And the United States government, namely the Navy, maintains atomic clocks on these satellites and make sure that they're all synchronized. And what you do when you're on your phone and you take it out to figure out where you are is your phone is looking for at least 4 satellites overhead. And if you can get at least 4 signals from these satellites that are telling you what they think the time is, you need 4 for X, Y, Z, and a 4th for time variance. You can do trilateration. So that's all happening on your phone today whenever you pull it out. And if it might take a few moments to find your location, it's because it's searching for these signals. And so GPS works really amazing. I don't think anyone would disagree that you can find out where you are at any point. But what's important to think of is in GPS, the GPS satellites themselves, they don't know where you are. You don't actually speak to the system. You don't communicate with it. And so when it comes to location verification, if all I do is get this signal on my phone, I can then change that data on my phone and pass it on to someone else. And that's called spoofing. And so because there's no history of my location, I never talked to the GPS, I can just lie about my location. And we see this happening with Uber drivers as well as in Pokemon Go. But in Foam's case, when we think of a permissionless, decentralized, smart contract-driven economy, if there's no way to verify that data and there's money at stake, anyone could just lie about their location. So that's kind of was the starting point for that project. And in kind of most recent year, we've seen a kind of explosion of articles pointing out how vulnerable GPS is, how it's susceptible to jamming, it's susceptible to spoofing, and there is no real backup plan in place. Businesses think it should be the responsibility of the government. The government thinks that they should just maintain the satellites, and it's the responsibility of the businesses. And this is something that we took really seriously, and it's a kind of a latent problem in existing industries today, and will be a larger one if we have these kind of decentralized marketplaces. So I'm going to dive into now Foam a bit, and this is one of my favorite diagrams, but it might take a few moments to understand. So each triangle is kind of this large category. So the one on the right, let's just think of GPS. It's this kind of whole infrastructure that many people rely on. Ultimately, we have these end users and applications. But because that GPS doesn't work that well indoors, for IoT, it takes up a lot of battery. It could be spoofed, it could be jammed. All these industries have to work in this kind of enhanced GPS domain. What that means is the system isn't good enough on its own. So you have companies like Uber spending hundreds of millions of dollars trying to develop spoofing algorithms to kind of detect people. Companies like Pokemon Go, they're trying to detect people. So they all have to use this kind of enhanced GPS to make their system secure. And every individual company, whether you're in a supply chain or in IoT, has to solve this problem individually. because you don't want to help out your competitor. And so that's kind of how it works today, where people have to have this middle layer to make GPS really work for their systems. When we look to IoT, IoT is kind of a massive field in its own, but there's kind of this subcategory called LPWANs. It stands for Low Power Wide Area Network Radios. And there's one we're really interested in called LoRa. But when we look in this IoT domain, they can't just rely on GPS. They don't have their own location system. And so they're kind of connected in this way, in that these low power radios also have to rely on these kind of augmented GPS data to really operate. And so where foam comes in is we want to take these components that no one's really utilizing in that way, namely these LoRa radios, which I'll get into, and serve that directly to these applications that are relying on GPS. And so no one is really tackling this problem head on and trying to offer a whole new location kind of alternative, and that's what we're aimed to do. And the way we want to go about it is a system that relies on synchronized clocks and using triangulation systems. It'll be made of low power radios. It's driven by cryptographic economics and incentives, and we have different kind of consensus algorithms through the system. And the point of the system is to be Byzantine fault tolerant. If you're not familiar, it essentially means it can run in a decentralized way and survive a number of nodes failing or trying to attack you. The goal is to have it work completely independent of GPS. We're not trying to replace GPS, and you probably would still use it to potentially navigate, but this is a system to generate proofs. So in the same way that GPS works, it kind of works in the same way in terms of physics, in that you have at least 4 nodes maintaining time synchronization. But the difference in this scenario is when the customer, we call them, finds their location from these signals, they can also speak back and basically have the system log their location. And the only real way you could ever generate that proof is if you were physically near these beacons and could communicate over radio. So the tenets of the system is that it should be trustless, independent, and open for anyone to join and participate as a network operator. But also you can be held accountable if you're caught cheating or attacking the system. And ultimately, we want to drive the network coverage through incentive models. So the time synchronization protocol we're developing at Foam is a software project. So ultimately, it's radio agnostic. It could run on all different kinds of radios. But we're really interested in ones that are cheap and accessible, so they're available for consumers, but also ones that operate on the ISM band. ISM is the radio spectrum that the government reserves for industry, et cetera, where you don't actually need a license. So we want to have one where anyone could join in a permissionless way, like Bitcoin or Ethereum. And in the kind of radio options, there's kind of this new type of radio that has come up in the last few years, specifically geared towards IoT, called low power wide area networks radios. And why they're so interesting is because they have extremely long battery life, but they also go an extremely long distance. And specifically, the radio that we're developing on at Foam is called LoRa. It uses a chirp spread spectrum, and it's found in many kind of IoT applications today. In kind of the best case scenario, it could go up to 10 miles and have a 10-year battery life, probably much less in an urban environment. And when we look today, we actually see people running these LoRa radios for kind of DIY projects already. So for us, that shows us that there are kind of people, consumers who want to participate in radio-based networks. This is a screenshot of Sydney of people running LoRa devices as part of a Things network community, which is kind of a hobbyist IoT network. This is Zurich, where it's maybe one of the most popular places of just people running these radios for free today. And we can see other kind of projects. There's one based in New York called the GoTenna, which has a consumer device to be able to communicate through mesh nets without cell. And this is, again, just showing that where people are hosting those devices. So we see there is this kind of consumer demand to participate in these kinds of networks. So just as a visual, in the Foam system, we're going to have these zone anchor beacons deployed across a city. And when they run the protocol, they're going to synchronize their clocks by running our time synchronization protocol and discover each other almost in a mesh fashion. And then they are going to establish these zones. So a zone is of at least 4 nodes. And when you establish a zone, you also need to stake tokens on a blockchain. And you can think of that as entering into a service level agreement, an SLA. So you're basically putting up collateral and saying, we promise to operate this zone correctly. We're going to maintain a quorum on time and space. And because of that, we'll be eligible for rewards and revenue from our customers. And then when you have a customer, it could be a car driving around. Let's call it Uber. And in this decentralized Uber, they're going to say to the driver, for you to get paid at the end of your route, you're going to need to generate these receipts along the way. And the only way that car could generate these receipts is by being there and communicating over radio with the zones. So where we are today, we're currently been testing those radios and determining that they were appropriate for the time precision needed. But just as a software project, the time synchronization protocol, the blockchain architecture is all software only. So we first built a kind of simulated testnet, what we call the GeoPickle. And it is a server rack of 40 Raspberry Pis, and this allows us to simulate the transport layer of radios so that we can just run the time sync protocol over 40 devices in one location. And this gives us a lot of great benefits because you can do things like the radios can hear each other only 80% of the time, or every fifth packet gets dropped, and we can see with these kind of errors what actually happens without going out into the real world. And these are just some documentation of when we were making it over the past 6 weeks. No one really racks Raspberry Pis in such a fashion. We had to get these interesting things called Bitscope Blade Quattros, and that was for us to rack those Raspberry Pis. And it was really convenient because the racks come in 4 slots, and for us, a zone is a minimum of 4 zone anchors. So for each Blade Quattro rack, that represents 1 zone in our system. This is just more for illustrative purposes of us building that. And that's kind of what it looks like in some fashion. Yeah. And so here is like a diagram of this testnet where we have this switch, and each blade represents a zone anchor. And so we're making really fantastic progress testing our Ethereum scaling solutions, things like Plasma, counterfactual verification, the time synchronization protocol, all within our lab. So that's really exciting for us and allowing us to make a lot of progress. And for example, what we actually see when we run these things is that we're actually tracking the zones on our dashboard, and they're running the protocol, and they eventually either synchronize or not. And so we can run all different types of scenarios, which is really cool. I think this is kind of a repeat of what I've just been saying, but it allows us to kind of simulate the time synchronization. And what we're doing next is we're now developing a custom firmware for these LoRa devices that would allow the phone protocol to speak to the radios. And once we have this firmware, at some point in April, we'll be able to move off of our GeoPickle testnet onto these radios and begin setting up testnets here in Brooklyn. And after that, we'll be specifying a foam developer board and basically be able to put them in the hands of all our community that wants to participate in testing the system. So that was all kind of high level in some sense and not that much illustration. So I'm going to end with a short video that kind of explains our system and vision a bit more. So as I mentioned, in the system you need at least 4 beacons, and 1 beacon is called a zone anchor. To participate in the system, you need to stake tokens as collateral into this service level agreement. And so when you have those 4 nodes, they'll search for each other, find each other, and they'll all see that they all have stake tokens, so they're all have agreed to participate in the protocol, and they can then synchronize their clocks. And so here we now have a zone that's kind of just there, it's promising to be there, and running this time sync protocol. But then this is an abstract, but you have a customer, could be a person, it could be a car, could be an IoT device. And when it's in the zone, it can find its own location, but then it can speak back, as I've been saying, and generate this, what we call a presence claim. And so a presence claim you can only purchase by being actually there, interacting with the protocol over radio, and signing that message with a cryptographic signature. Now this data is then stored in the zone's logs. The zone's constantly synchronizing and keeping logs. And those logs are then inspected by verifiers. So these verifiers check for fraud proof and run all these kind of different geospatial kind of algorithms to make sure nothing's breaking the laws of physics. And ultimately that data gets stored on the blockchain. It's final, and it's owned by you, the customer. So no one can see that data. You get to choose who you want to reveal it to. You could keep it secret, you could reveal it to an application, you could reveal it to the FBI when they show up and ask where you were. And some applications that we imagine, like I said, is mobility. So you're going to have different use cases where people have to show where they were and generate these proofs. Also gaming, in that you can unlock rare assets when you go to these locations, which was a big problem with people attacking Pokemon. And also supply chain is another huge one where along different points of a product's life cycle, you would be able to determine where it actually is and have kind of the cryptographic fraud-proof assurances that that is the case. So that's all. We are Foam. We're based in the New Lab, which is a tech facility based in the Brooklyn Navy Yard, where a lot of interesting stuff is happening. There'll be some events there during Blockchain Week in May that we'd love to see you guys there. And thank you.
I think we got time for like 2 questions. Oh, someone's hand is already up.
I'd love to hear a little more about how, like, say I've proven my location at a previous time, and later on, if I need to reprove that to some entity, like how I might go about doing something like that.
Yeah, so the digital receipt that you purchase, in our system we call it a presence claim, and once it's stored locally in the radios you spoke with, and their logs are checked for fraud, and ultimately the results are posted on the parent blockchain. Let's call it Ethereum for now. And the presence claim itself ends up as a first-class object on the blockchain, and you are the only one who can reveal it because you have the address with the private keys of that message. And so you're in control of how you would want to reveal it to someone else. You could do that, but it's more likely that there'll be these applications with their own architecture, and they will be defining the logic. So I'll just stick to the Pokemon game. They'll say, hey, you have to buy one of these at Times Square to unlock this rare thing. The idea is that application has probably many other logics as well, and from the end user, it could be a really user-friendly experience, but otherwise, it's something that you could only unlock because you own the private key of that receipt that you purchased.
One more question, and oh, sorry.
Why are you stuck with 4 anchors? Because the worse your clocks are, the more anchors you're going to need. And since, the GPS system has atomic clocks and 4 GPSs, why don't you try to generalize this to have more anchors?
Yeah, sorry, for the confusion, it's not limited to 4. It's just a minimum of 4 is required to establish.
And how stable is that to, the number of anchors? Like, let's say, because your clocks are not good, they're not atomic.
We would be use rubidium chip-size atomic clocks in the final product.
Okay.
Over to the chat now. So if you give us 2 seconds, we're going to put the chairs up.
Thank you, everyone.
And get going. Thank you.